We put you in the picture with what does a PLC do. Then we looked at the sensors or the input field devices, then the output field devices, then the hardware. Once we had all that done, then we talked about ladder logic diagrams, which is what resides in the memory of the processor of the controller. The next thing that we want to do is look at overall what is a PLC. Now that you have all the blanks filled in with all the individual elements, discussing what is a PLC is going to make a lot more sense. I refer to these as mood setting videos in the beginning. Hopefully, if you really want to learn this subject, that you should be getting more and more in the mood to get into the nuts and the bolts. So let's do that. Not what does a PLC do? We've already covered that in an earlier lecture, but what is a PLC? Prior to attending this lecture, you should have attended the lectures on what a PLC does. What does a PLC do, as well as input field devices and output field devices. If you did not attend those lectures, then you need to watch the recordings of those lectures and then come back here and continue. There are several other lectures that you could also watch first to enhance your understanding of this lecture. Those being PLC hardware and ladder logic diagrams overview. Now physically, a PLC is a piece of electronics with screw terminals for both power and interface to the external process or machine. This is a Micro 810 controller. We represent the inputs and outputs available with this particular controller. The area of focus for the PLC is random access memory, or RAM. Everything of interest takes place in the memory. Within the RAM, there are two areas of interest: machine-specific coded instructions and data. This is what we will cover in this lecture. Let's begin with the input field. The input field represents everything from the screw terminals out to the process. We run 24 volts DC out to the process, to the machine. It powers sensors and information comes back to these screw terminals. The field devices at this point are irrelevant. You would have learned about those in a previous lecture on input field devices. This is our input field interface, these screw terminals. We mention these screw terminals quite often in our presentation. This is our output field devices, screw terminals. This is a Micro 820. What you're looking at is a controller. By the way, you might also refer to a hardware platform that has a separate power supply, separate processor, and separate I/O modules as a controller once it's assembled, because the data structure, the electronic structure of a controller like you have in front of you, where everything is embedded inside of one plastic housing, and another instance where you have a power supply with a processor attached to it, I/O modules attached to that. You can also refer to that as a controller, but we call that modular as opposed to fixed I/O. Now this processor, you can expand and add more I/O modules. Let's bring our RAM back into view. So here's our random access memory. Very important, also we added communication ports. Now we switch to the Micro 820, which has two ports. It has RS-232/485 and it has Ethernet IP. So one port will support 232 or 485. All the contact that you're going to make is to RAM via one of these COM ports. Downloading to RAM, online monitoring in RAM, and editing and uploading, not to mention flashing firmware if that becomes necessary. Now let's consider RAM. RAM is like a section of land, 640 acres, and let's say it's all clay and flat as a pancake, meaning that every square inch is identical to every other square inch in that 640 acres. Now, I don't know how many tens of thousands of square inches that is, but so this is a good representation of a memory array. So every square inch is identical to every other square inch. It is all the same, and so is every single bit in this memory array until we map it out. Let's discuss how Connected Components Workbench maps out the RAM. Now keep in mind that this controller, or rather its processor, has firmware. And firmware, they also sometimes call it executive software. So what you download into the RAM is subject to control by the executive software or the firmware. But let's stay away from that. Let's just talk about the RAM, the part that's volatile in a sense, the part that you download to. And primarily you have two sections mapped out, global variables and programs. We divided it up into two boxes. Global indicates that all programs have access to all of these variables, and they are strictly data tables. So everything inside of that larger box that says global variables, and then inside of that you have I/O variables, user global variables, system variables, and defined words. So global indicates that all programs have access to these variables, and again, they're strictly data tables. There's no methods inside of the variable files. They are just memory locations that you have, or the manufacturer has, created a name for, defined it, and it pointers, variables, tags, whatever you want to call these memory locations. All those names are usable, and we will use those interchangeably throughout this course. Specifically, Micro 800 calls them variables, but you could also call them pointers because they point to a memory location. Remember, memory locations are numerical, or you can call them tags or tag names. Besides a name, you have to define them with a data type. Programs contain all of the coded logic, and each program has its own unique and isolated variable file. So you look at the separate little rectangle, it says program, and then local variables. The local variables, which is a data table, they are only accessible from within that program. You cannot access the local variables from anywhere else except directly through this program. Global I/O variables are determined by the embedded I/O count and type, and any plugin or expansion modules. The types are fixed because they are module-defined data types, which means the electronics has a fixed data structure. It's all pre-named and all predefined. So the I/O variables, you cannot edit those. You can change the size of that data table by adding or removing expansion or plugin modules. User global variables are the variables that you name and define the type. These are variables that you want to make accessible to all programs and all external entities outside the controller via the COM ports. In other words, if you want to access variables in this controller from an HMI or another processor, another controller, it's advisable to create those in the user global variables, not in the local variables. Keep in mind that global variables means that they are accessible to all the programs and to external devices. Now, discussion of system variables and defined words is outside the scope and the time limits of this presentation. Something else to note, you can add up to 256 total program files, each with its own isolated variable data table. So there I show 3 of them and then some little dots in between to indicate that you can add a lot more. In the older platforms, you can divide up your code into multiple programs, and they will execute in the order that you place them in your project view. Each program has its own local variables. So there you see 3 rectangles, each with local variables. Now, in the global variables upstairs there, let's say user global variables, you cannot create 2 variables with the same name. That would be a conflict because that same name can't point to 2 different memory locations. But in the programs, they each have their own local variables. So every program can have a variable with the exact same name that the other programs do, because each program can only access the global variables and its local variables. So the second program there, it can access the global variables and the local variables within that program, but it cannot access the local variable data table of any of the other programs. For example, you could write a program for a conveyor. Let's say you have a conveyor system, you're sorting cartons onto spurs. And these spurs, you're going to sort products of the same type out onto a spur, and once you have enough to make a unit load, then you're going to push that on down to another trunk that's going to go to a unitizer, a palletizer, and make up a unit load of that particular product. And let's say that you have 10 conveyors, 10 spurs. You can perfect the program for one conveyor and then copy, paste it into another program. And the only change that you have to make with each additional program is any use of global variables, like I/O variables. Obviously, you can't use the same memory location for the same photo eye in all 10 conveyors. that means that you're going to have to go into the program, not the local variables, but to the program and edit the I/O variables and any other user global variables that are germane to what we're discussing here. And as I said, you can create up to 256 of these programs. So that gives you quite a bit of granularity. Let's focus in on the interaction between code and the program file and these various locations of data, these various areas of memory. Let's assume that we have downloaded a project into the processor's RAM. Remember that the processor is a separate section of the electronics in the controller. So if you say controller and processor interchangeably, you can get away with that. It's always a good idea when you're referring to the electronics that does the processing, that has the RAM in it, as the processor. If you say in the controller, it's just assumed you mean the processor RAM. Here we have a rung of logic. In an earlier lecture, we discussed the origins and logical nature of ladder logic diagrams. If you have not attended that lecture, you should watch it first and then return here. It is absolutely that you understand the nature of relays. Well, you don't have to. You could just fuss your way through it. But the more you understand about relays, the more these rungs make sense, even though you're not going to be using relays. We have 4 instructions here, which their true-false state determines the on-off state of a bit in memory. Of the 4 instructions that determine the action of the 5th instruction, they are a direct contact, which is true if on. It is addressing the embedded input 4. Then we have a reverse contact, which is true if off, and it is addressing the auto mode bit in memory. And then we have another direct contact, which is a true if on, another direct contact true if on. So the first one, true if on, is true if that bit in memory is on. They call it a direct contact, and they call the second one a reverse contact. But I just cut right to the chase here and say the first instruction is true if that bit in memory is on. The second instruction is true if that bit in memory is off. And you're thinking, well, why do you need that? Well, think about this. If you have a conveyor and you have a photo eye at the entrance, you might want to make a different decision based on whether it's blocked or it's not blocked. And let's say it's on when there's an object in front of the photo eye. And let's say when there's no object in front of it, it's not blocked, then it's off. You don't want to put something in that spot if there's something already there. But if there's nothing there, then you want to put something there. So you need true if on and true if off, especially like the auto mode. This says if you're not in the auto mode. Well, if you're not in the auto mode, then you don't want to execute this logic that's going to turn on output 6. So we have a total of 4 read type instructions. Each of these first 4 instructions read a memory location, and then they are either true or false. They actually are statements, not queries. So in a sense, the first instruction says input 4 is on. That's either true or false. It's in the auto mode, true or false. It's in step 2, true or false. This is the first program scan, true or false. Finally, we have a 5th instruction that is a direct coil, which has a true execution and a false execution. So let's consider each instruction in the order that they are scanned, keeping in mind that the 5th instruction really is a write instruction. It doesn't make a statement that is either true or false. So the first 4 instructions are never on or off. They are true or false. Consider the first 2 again. True if on, true if off. So the first instruction is true if the bit memory is on. The second one is true if the bit memory is off. That's why when you look at these instructions, you always want to keep in your mind they are never on or off. They are true or false. Now the bits in memory might be on or off, and that determines whether they're true or false, but they're true or false, never on or off. And then the 5th instruction is never true or false. As a matter of fact, it's not on or off either. It is just a write instruction that if it's true, it does something, and if it's false, it does something different, just the opposite. Let's consider how these instructions are scanned. Let's take the first one. The first instruction, direct contact, true if on, reads the state, the on-off state of a memory location that it is addressing. If that bit in memory is on, then this instruction is true. I just want to stop and beat a hobby horse here for 1 second or 2, and that is that address was originally just a verb. You addressed an envelope to a postal location, you addressed an individual, or you addressed a group. But the group was never an address, and the postal location was not an address. It became a noun through misuse of the word over the years. If you want to call it a memory address, that's fine. I think it's better to say memory location if you can break the habit, just to avoid any confusion depending upon who you're speaking to. So, The first instruction, direct contact, true if on, reads the state of that memory location that it is addressing, which is underscore IO for input output, underscore EM for embedded, underscore digital input, DI, underscore 4, which is the 5th input, because it starts with 0. 0, 1, 2, 3, 4. That's 5. That's the 5th input. If that bit is on, then this instruction is true. Consequently, if that memory location is off, then the instruction is false. That memory location is located in the variable data file, and you see that we're reading from the IO variables. The second instruction, a reverse contact, true if off, reads the state, the on-off state of the memory location that it is addressing. If that bit is off, then the instruction is true. Again, that second instruction, reverse contact, true if off, reads the state on-off of a memory location that it is addressing. If that bit is off, then the instruction is true. Consequently, if that memory location is on, then the instruction is false. So here's where I like to point out why I call these true if on, true if off. It just cuts right to the chase. Reverse and, direct contact, reverse contact just don't do it for me personally. Now, that memory location is located in the user global variable data file. This is a variable that you named and defined. You define the type and the scope. The scope means where it's placed. So if it's globally scoped, then it's going to be user global variables. If it's locally scoped, then it's going to be local variables. The third instruction, Step 2, that's in the program local variables. So when this instruction addresses or it makes the statement Step 2 is on, it has to read it from the local variables. If it's on, then it's true. But if this bit in memory identified as Step 2, if it's off, then this instruction is false. And again, the memory location is located in the local variables data file. And you can see why I laid it out this way. So it gives you a sense of, even though it's one rung of logic in a program, that we have a rung of logic that's going to read from 4 different locations. And so the next one, system variables first scan. Now never mind what this is. Well, I'll just tell you. This bit is true for one scan and one scan only when you go into the run mode. And this is a really nice bit to use if you want to tidy up your data table values in a situation where you had a power failure or you had to go into the program mode to make changes or you shut the system down. You want to go up in the first scan bit. It's only going to be on, which means this instruction is only going to be true for one program scan, and you can use that to determine whether or not logic gets executed. Just looking at my rung right here, this rung would only be true during the first scan when you go into the run mode, okay? And the memory location is located in the system variables data file. Now, I have system variables and defined words kind of grayed in a sense. The system variables, its entire data structure, its wireframe of data, if you want to call it that, is based on this controller, on a micro 820. Now, you see I say any micro 800 controller because the format's the same, but the actual system variables could be different between an 810, 820, 830, 850, and 870. And by the way, I walked away from the 810 right away in this lecture. The micro 810 is all by itself and does not have the portability between controllers or processors that the 820, 830, 850, and 870 do. So from now on, everything I do is going to be 820 or up. The last instruction, fifth instruction, a direct coil writes to the memory location that it is addressing. If the wrong collectively is true, then it writes a 1, or rather turns that bit on a memory. Consequently, if the wrong state, the overall state, is false, then it writes a 0 to that memory location or turns it off. Now, we started with an input variable and concluded with an output variable. We started by reading something from the IO variables, and then we concluded by writing something to the IO variable. That wasn't really on purpose. So it's very important that you understand it would not matter in what order the first 4 instructions are in. They must all be true to turn on that output bit. So you could place these 4 instructions anywhere you want in the series. They all have to be true. So it doesn't matter which one's first, second, third, or fourth, as long as they are ANDed in series like they are. Not all rungs require instructions that address all these variable locations. Some rungs have instructions that address just local variables or any combination thereof. So you could have a rung of logic that is addressing strictly bits or values in the local variables and then writes a conclusion to a bit in the local variables. As far as the system variables go, those are for the most part read-only. The primary ones you're going to use are I/O variables, user global variables, and local variables. System variables and defined words you're not going to have much use for unless you get into something more advanced. Oh, so there we got it, a Micro 820 controller, the whole 10 yards, the whole ball of wax, the whole shebang. Input field devices, that's input module, or built-in embedded, a processor with RAM, then output field devices, either as modules or embedded. And remember that the 820 has 2 plug-in slots on the face of it. So you can plug in 2 additional I/O modules of a whole variety. In the instant that you do that, of course, you have to synchronize that with your project. That then will expand the I/O variables data table to include some additional memory addresses that you address to work with those 2 I/O modules. Some Micro 800s, of course the Micro 810 has 0 expansion, but all of the other Micro 800s have expansion capability. I should say plug-in and or expansion modules. Expansion modules, they clip onto the end of the controller. They're not plug-in. Okay, now we got the whole picture, right? So if someone says, what is a PLC? You ought to be able to do a serious mind dump on them. you ought to be able to bore the heck out of them with more information they probably want to hear. But you need that information because it gives you more of a feel for what you're working with. And again, the whole idea was to put you in the mood to learn more about PLCs.